Okay, continuing with PaulGradenwitz response on ResearchGate. I'm going to clean this up by making layer 2 transparent. All right, part of the last video kind of got written over. Let's talk about this moving original ball. The moving original ball. The idea of the moving original ball, I think, can be described in this spacetime diagram as something that might have an initial velocity before the explosion occurs. So we might have a moving original ball that comes this way, and puts an explicit center of the universe at x equals negative ct over 6. Or we might have an original moving ball representing the center of the universe coming this way, which puts the center of it at x equals 0. Or an original moving ball coming this way. In any case, I don't think of the universe that way much of the time, although I think that if the mass of the universe is less than infinity, then you can find that all of the particles in the universe would have an average momentum. P average equals some specific velocity. What is let's see, MC beta gamma. It would be the sinh of some, then there would be some central rapidity that you could call MC sinh phi sub naught. And I can work with a universe that does have mass less than infinity and does have some central mass. I think the outside edge of that such a universe might be might appear from the outside. I'm not sure of this, but the outside of such a universe might appear as a black hole. And the other possibility, which is, and this type of universe I would definitely call a modified Milne. This would be a modified Milne model. In Milne's original description, the mass of the universe is infinite. There's no outer edge, so there is no average momentum equal to mc sinh phi sub naught. His description, he was describing a perfectly he was describing a universe that was consistent with a version of the cosmological principle. In the cosmological principle, there is no part of the universe. In the cosmological principle, basically there is no central rapidity. So there is no average momentum, and if there is no average momentum, then the mass of the universe has to be infinite. So this has different meaning. If you start with a moving original ball, that means the mass is finite, and you could have that finite mass have an average rapidity, this being the angle of rapidity. I'm sorry, I shouldn't draw it that way. I should draw it this way. Yeah, rapidity angles should be drawn this way. I think I've been consistently making that mistake all the time, but an angle makes sense to draw the angle like that, but rapidity should be drawn like that. In any case, I just wanted to kind of focus on that part of it that made sense. I don't know what, but I'm still not sure what he means by there is no difference. Because whether you have some moving ball of finite mass or you have an infinite mass, that does not affect the difference between this line and this line. Those two lines have different velocities, they have different rapidities, and there is a difference. But let's talk about this difference between PG's description and my description. And his idea is that time dilation is experienced. And my description is there is no experience. There is no personal experience of time dilation. And he says that the time dilation experienced is based on x equals 0, based on your distance from x equals 0, on your speed with respect to the origin. I say no origin is relevant to your experience, your personal experience. Well, actually, no distant origin. No distant origin. Your experience is based on your here, which is x, your x equals 0, and your now, which is t equals 0. And so it is based on that here and now experience. Your personal experience, del x del t equals 0. Del t equals 1. That's all there is to those two things. Your experience of the here is here. Your experience of the now is now. Then he says that dilation sets the absolute clock speed of its decay. And I was about to try to demonstrate that, but then crap, I just realized that last time I worked on this, I did not save the, don't think I saved it after I was done. Because I wanted to make shrapnel boundary events that were, shrapnel boundary events. I did record it though, so I can see what I did. That's pretty important. But the key to this thing was the speed, the number, and the time. The time was given in coordinates of the origin at x equals 0, and the main thing to apply here was cosh, whoops, can't spell, cosh of the rapidity, which would be arc tanh of v over c. And what happens then? What happens then is my computer crashes. Well, for one thing, I put v in there, and I should have said speed, because that's what the thing in the function is. It's all messed up right now, but you can see the things coming out, that you have events from different, you have events happening at different times. But when Paul refers to here of the decay, he is referring to something where several particles come out at different velocities from the origin, and they decay at different times on average. Now, if you have a whole lot of particles decaying, then I think this becomes almost perfect, because while one particle might decay at its half-life, but it's basically random around there. If you have a billion particles all decaying at the same average half-life, then you would end up having the decay happen almost in a very organized fashion across the universe. So in at least this part of it, Milne universe would be equivalent to the FLRW metrics, because you would have, whether that absolute speed of its decay is based on some absolute reference point x equals 0 at the center of the universe, or if all of these, or if you allow for the Lorentz transformation of the thing, it doesn't make any difference. It's going to be the same. So there's x equals 0, here's O, here's A, and here's B. Basically, not, this is line, this is the B trajectory, this is the O, this is the origin, this is the O, and this is the A. You can see, so he says, so when you take that point A and that point B, you've chosen the point B in the film, then they have the same relative velocity with respect to O, but because the point B is on the line x equals negative ct over 2, that's O's internal clock is running slower than the clock of point A on the line x equals ct over 6. Who, B's? B's internal clock is running slower? Yes, in this reference frame, B's internal clock is running slower than clock A on the line ct over 6. As a result, there is an intrinsic extra redshift in B that will come on top of the Lorentz redshift for O. For the observer O, the point B has more redshift than the point A. No. For the observer O, the point B has the same redshift as point A. Well, no, it doesn't have the same, but you know, it doesn't have the same because we haven't done these right. We would need to do not x equals ct over 2. We'd need to do x equals arctangent of 1/2 times c over 2. No, so just c. C arctangent 1 over 2. If we made times t, this is what we would want to do if we wanted to come out symmetric. But I could check this if you want, observer O, because if we are doing equipartition by velocity, then there is going to be a difference between the redshift of point A and point B. It's not, I don't think it's the reasons that you're saying, though. But let's compare these two things. C over 2 versus arctangent of 1/2 times c. Okay, arctangent of 1/2 is slightly larger than arctangent of is slightly larger than 1/2. So if we want to compare these things, we would have 0 v equals 1/2, and then we'd have over here a little bit further v equals arctangent of 1/2. And the arctangent of 1/2 would be moving slightly further away. So the region, so over here we've got, actually, if we're actually going to use v equals 1/6 over here, we wanted to find this the region that has the same redshift as this object, or the place where that, so we'd first have to take tanh of 1/6 over here to figure out what the rapidity was, and then add this velocity plus tanh this velocity here, v equals 1/6 tanh of 1/6, and that would be the difference in rapidity between this spot and this spot. And then to find over here the spot that has the same rapidity, we'd have to double it? No. Anyway, I'm not going to finish that problem right now. I'm going to get back to Paul's description, but the point is you can fairly simply find the region over here to look for to find the same redshift, but it's not going to be this point. I do agree that if you use CT over 2 and negative CT over 2, and this is CT, or yeah, this is not going to come out as an equal redshift with this because you're not properly applying rapidity. In rapidity space, it's quite easy. But in velocity space, it's kind of like adding slopes. If I said, let me make up an equivalent problem with slopes. I'm going to take two wedges. This one has a slope of 1/6. 1/6 equals y over x. Then I'm going to take another wedge, again with slope y over, I guess this is not going to be as long. We'll make that x just a little bit shorter, and I'll call this y over x. And I'll say that y over x here is also 1/6. And then it was supposed to be the same triangle, but I didn't quite draw it exactly to scale. Anyway, what's this point then? Is this going to be y equals, well, down here we can make the statement y equals 1/6 x. And here we can also say y equals 1/6 x. So can we take the total? Y total is 1/6 plus 1/6 x. No, we can't. But if we make these things into wedges and say this angle is arctangent of 1/6, and this angle is arctangent of 1/6, we can, at the end, say y equals r sine arctangent of 1/6 plus arctangent of 1/6. So we can say y equals r sine of 2 arctangent of 1/6. And that should be why your round 2 does not go through B, because you're adding slopes together to get 1/6. Yeah, these are adding slopes, 1/6, 1/2, and 1/6, 1/3, and 1/2 are adding slopes together, and when you add slopes together, you don't get a even formation. Okay, then when observer O starts to search for objects that have the same distance, he searched for objects whose light travel time was the same. With your lines of simultaneity, okay, so if he started to search for objects whose light travel time was the same among these lines, guess what? Among the things that came this way around O, he would not find any. I'm sorry. Yeah, that's right. He would not find any objects that had the same light travel time between here and here, between here and here, and here and here. That is not. He's not going to find any. Not in any of those rounds. All right. Once again, I have reached the 20-minute limit, so I am going to bid you farewell.